Great. Thank you. It's a pleasure to be here, and it's an honor to speak in the same session as Yair Shokef. I was remembering yesterday that my second ever paper, the Yair was the first author of. He was the one to write it, and I hope you'll see maybe some of what I worked on then was maybe more related to frustration. You maybe see some of the remnants of that in my talk. What I wanted to tell you about is actually not entirely unrelated to the first talk. I'll also talk about mechanical metamaterials, but there's a sort of one caveat, one difference with what Yair has talked about, which is that I'll tell you about active mechanical metamaterials that aren't just static structures, but have some sort of motors in them. And most of what I'll focus on is in this recent preprint. And the preprint is called More is Less in Unpercolated Active Solids. So the first thing I'll start with is why more is less is interesting to us. And this has something to do with something old and probably very familiar to all of us, which is Le Chatelier's principle, which is often introduced in thermodynamics to kind of say that a system at equilibrium shifts to counteract an external stimulus. But that's really a consequence of having an equilibrium at a potential minimum, right? So it applies in a sense to some mechanical systems as well as thermodynamic ones. And again, it applies when you have a mechanical potential that you can define. In particular, one of the kind of very basic consequences of this principle that's very intuitive for us is comes in the micro-macro relations that we think about in elasticity, which is that if we have a material here, this is the extent of my own experimental expertise. If you look push on a piece of rubber or take some sort of a structured material, and you say, well, I'm going to take one of the components of the material, I'm going to make it stiffer, right? And I'm going to look at linear response around that. The consequence will always be that the material is at least as stiff as a whole, right? And usually stiff. This applies to materials, also applies to structures, right? So when you build a bridge, when an engineer builds a bridge, they want to make sure that if they replace one of the beams by a stiffer one or a thicker one, that the whole bridge won't fall apart, right? That it'll be at least as structurally sound, and that's a kind of an important underlying principle, perhaps a little bit too trivial to kind of think about it too hard, but we can sort of outline a little proof of why this happens, essentially, when you go from the micro to the macro scale, right? And the little proof sort of relies on defining a potential energy here for some sort of a structure where you have a set of displacements on the nodes here. You have a set of spring constants that relate your displacements to a potential energy. And one of the key kind of assumptions is that, first of all, there's a quadratic potential, and then also all of the spring constants are positive, right? You have a positive definite potential energy. So when you go from this kind of micro scale to the macro scale, all you do is that you take this potential energy and you minimize over all of the non-affine deformations to get a stiffness tensor, the elastic tensor here, in terms of the affine displacements, or the affine deformations, where all of the particles kind of follow the global strain field, and take the non-affine motions, all of the other motions here, and minimize the energy over them, right? This minimization is the same thing as saying that you have an internal force balance, that no residual forces are present in the system. And this minimization step is the kind of important key feature here that tells you that if you increase one of the spring constants here, then after this minimization, when you look at this elastic tensor here, the eigenvalues of this tensor, which we can think of as elastic moduli, will increase monotonically in the microscopic. Okay, so this is perhaps all very obvious and very intuitive, but what we want to do, what a lot of us do in the mechanical metamaterials community, is to sort of think about things that happen in, well, for example, in equilibrium here, and try to break it, right? And that's maybe less obvious. Right? In particular, that I said that having a potential minimum is a key ingredient, right? But just if you don't have a potential minimum doesn't necessarily mean that you will somehow break this micro-macro relation in an active material. So what I like to think about is the more kind of constructive proof that this doesn't always. And so, as I said, what I wanted to focus on are active mechanical metamaterials, in particular a type of activity that I'll refer to as non-reciprocity here, that's sort of illustrated in the video here. This is the experimental system that very much inspired us, and where some of the things I'll talk about have been realized. So in this experimental system, what you see are two motors, right? And the special thing about these motors is they communicate with each other, and then they exert, they sense their own angle, right? Pass this information to their neighbor, and then the neighbor decides based on θ1 what the torque on the angle θ2 should be. And because these are motors, because these aren't just elastic spring, the torque can be arbitrary, and in particular, it can be non-reciprocal, and this is what's shown here, right? So you increase θ1 in the beginning, and θ2 increases. But if you apply, change the angle θ2 such that increases, θ1 decreases. You now start to make little hexagons, little unit cells out of this material. You can sort of translate it into thinking that the torque on the active component of the torque on one of the particles is the difference between the changes of the two neighbors' angles. Right? And the fact that it's a difference rather than a sum is what makes it non-potential, and the prefactor here can be thought of as a kind of microscopic active spring constant, right? Our microscopic parameter that determines the mechanics of this. And of course, now you can go from this single hexagon to the continuum scale, right? And think about what happens if you make a material out of these non-reciprocal springs. And to do that, maybe the first thing to do is not to just start coarse graining things, but think about the symmetries that come about in the system. And if you have a two-dimensional isotropic material, if you have energy conservation, if you require to be reciprocal, right, made out of normal springs, then you're sort of guaranteed to restrict yourself to just two elastic modulus in this elastic constant, that elastic tensor that I've already mentioned, right? So this is just a funny way of writing out this elastic tensor, where I have a strain field here that I've decomposed into 4 components in 2 dimensions, and a stress field decomposed in the same way, right? So in particular, the top row here is the pressure in the stress and the volumetric dilation in the strain. And the relation, the proportionality between those two is the bulk modulus, which is the inverse of the compressibility and common to both fluids and solids. What sort of defines an elastic solid then is this other number, which relates a shear strain here to the same shear stress. And this proportionality constant is the shear modulus that that we're all used to, and these are the only two numbers that can enter this elastic tensor. In particular, there's no this is the rotation line here, and there's no stress due to rigid body rotations and no torques due to any strains here. So now if we kind of keep the structural symmetries the same, so we keep it two-dimensional and isotropic, but break this requirement that we're reciprocal or that there's no energy being injected into the system, then the moduli that you can have in this elastic tensor, expand, right? There's one more number here under the same assumption, by the way, that you still have no stresses due to rigid body rotations and no torques. There's still one more elastic constant that can appear in your system, right? And you can think of this as the non-reciprocity that I showed in the microscopic case, but now at the continuum scale, right? This is a non-reciprocity between the two directions of the shear that you're allowed to have in the lattice, and we call this non-reciprocity odd elasticity due to a historic kind of analogy with what someone else called odd viscosity. But anyway, so the reason that I say it's sort of non-reciprocal is because you see that this enters the antisymmetric component of the elastic tensor, right? That, unlike our kind of passive moduli. And so what you can think of this here, so it also enters just the shear components, right? It couples the two shear directions. The two orthogonal shear directions are with respect to at 45 degrees with respect to each other. So now what this means is that if you take a material and you shear it along the horizontal and you measure the stress, you'll measure the stress with some sort of a sign here at 45 degrees. But now you take the material and shear it 45 degrees, and you measure the stress back along the horizontal, and you get a negative sign, right? And this negative sign is sort of the same kind of negative sign that I had in the, I emphasized in the torque, and that's the sign of the some sort of underlying activity, non-conservation of energy in. And of course, what we want to play around is with this micro-macro relation, right? So now we want to go to maybe before I go to this. So I'll talk about robots, but there's been a bunch of systems that are chiral in some way and elastic, and in several of these odd elastic coefficients have been measured explicitly. I'll emphasize the spinning colloids here, this piezoelectric system, the starfish embryos. But anyway, so now what we want to do is to go back to the kind of microscopic system, right? This hexagons made of robots, and tile it into a lattice, right? And then figure out what the odd modulus is for this lattice, how it's related to this microscopic activity, and what sort of micro-macro relation you get for these different configurations. So this is a particular lattice that was made in the lab. So this was in Anton Souslow's lab in Amsterdam, where you do in order to measure the elastic modulus here, K naught, is to shear the material. You saw this video playing earlier, so you apply a simple shear. And if you had a rheometer, right, you apply a simple shear and you measure the tangential stress on the top surface. But here, it's not a usual rheometer you want to use. You instead want to measure the normal stress at the top due to the simple shear, and this coupling between the normal stress and the simple shear is exactly given by this odd elastic modulus. So you can directly measure this odd elastic modulus by dividing the two out, right? Divide the stress, the normal stress, by shear. And so you can do this experimentally. I'll tell you in a little bit how, what exactly these theory curves correspond to, that can do this exactly, and the two seem to agree fairly well with each other. So, for example, when you have no activity here, right, you see that it means that you have no non-reciprocity here at the microscale, and this also means that you have no macroscopic odd modulus. Also means that if you look at the kind of spatial distribution, right, of these shears, you will only get the shear 1 here, which is the one you've applied. That's the simple shear, and no shear 2, which is the orthogonal one, which would be coupled by these active numbers. Now, if you go to kind of start cranking up the activity, what you'll see is that this deformation field changes slightly, and that you have this odd modulus appear. Right? So you're now sitting somewhere along this curve, and in particular, you see the appearance of this orthogonal shear direction in the deformation. And the interesting thing comes about is when you crank up the activity even further, where the deformation field changes a little bit, but more importantly, you have this saturation of your macroscopic odd modulus with activity, and then the further theoretical decrease, right? Where now you're in this regime that that's counterintuitive, where you're making the microscopic active component stronger, but overall, when you're measuring it at the macro level, you're measuring something weaker, a weaker active response. And you can see that here with also the decrease, for example, in this orthogonal. So what is happening here, right? This seems to us like the particularly interesting regime, and we wanted to kind of dig into this a little bit, and we can dig into it a little bit better in simulations and theory, where we can sort of discard the effect of, for example, the boundaries, right? This is an infinite system, and see how the deformation changes for this specific lattice. It's the same lattice as in the experiments, as we crank up the microscopic activity. So what you see here is that when you have no activity at each individual hexagon, these are the hexagons in circles, then every hexagon is the same, and so the system deforms affinely as a whole. But as you start to crank up the activity, the active hexagons, again, the ones with the circle, deform in a different way from their passive counterpart, right? And eventually, is when you go to this kind of very highly active regime that's, as I said, non-monotonic, right, where you have a decrease of the overall active modulus. What's happening is that these active hexagons stop deforming entirely, right? You see in this deformation field, the color corresponds to the amplitude of shear strain, and these active hexagons stay. And of course, if you're not deforming these active hexagons, there's no active response to be measured on the macro scale. All right, so that's particularly interesting. But also, one of the things that's interesting is, does this always happen, right? Is this somehow structurally dependent? And the answer is yes, right? So you can take a slightly different lattice, one that has slightly more active hexagons as a whole, as a fraction of the system, right? And have a completely different macroscopic response as a result. Right? So when I play this video, what you'll see is that in this lattice, these active hexagons do not deform, and so if you track this odd modulus as a function of microscopic non-reciprocity, you have this behavior that I showed in experiment, where you saturate at some maximum, and then as you increase the microscopic non-reciprocity, you decrease the macroscopic response. But in this lattice, right, only slightly different, you have a purely monotonic behavior. In fact, it's linear, right? You make the material microscopically more non-reciprocal, and you get a larger non-reciprocal macroscopic response, where every single hexagon, independent of whether it's active or not, deforms in the same way, and therefore all of the active hexagons contribute to the macro level. So the fact that there's something interesting that happens between these two lattices that's that are very similar to each other, that don't seem to have that dramatic of a geometric difference between them, made us think that maybe there's some sort of a transition between them. And so we call this kind of a transition an active percolation transition. It's similar, in spirit to either a site percolation or rigidity percolation in some way, although it refers to the percolation at the level of this active modulus. And before I go into why we call this a transition at all, I wanted to say that this suggests kind of a very basic design principle. If you want to have active mechanical metamaterials, active materials that have a macroscopic response, then what you want to do is probably to use as few robots as possible, or as few active components as possible. But you can't use too few, right? So you want to use to add active plaquettes into your passive lattice until just above this percolation transition, and then you'll be able to get away with using few active components. Maybe actually, let me see, how am I doing on time? 10 minutes. With question. Okay, great. All right. So then let me tell you why we thought it was an active percolation type transition, which is rather than looking at different order lattice structures where it's difficult to tune the fraction of active hexagon, you could look at the disordered case where you randomly place these active hexagons, and then you are able to tune through this transition continuously. And indeed, you see these two kind of extreme regimes: the affine active regime at high filling fraction, the very non-affine passive regime where these active hexagons are isolated here at low filling fraction, and something interesting and heterogeneous happening in the middle, where you see all sorts of clusters of deformations, right, and different degrees of deformation of these individual hexagons that tell us something interesting might be going on here. So you can kind of plot these deformations on this axis now of dilution, how 1 minus the fraction of the active hexagons. And you see this percolation transition here, that it happens quite sharply, where you go from a very low emergent response here at high dilution to a large emergent response at low dilution at high filling fraction, where significantly on this side your odd modulus grows with the microscopic activity here. So these are 3 different curves for 3 different microscopic activity, and it doesn't happen on this side. Moreover, you can kind of see other signatures of the transition here, where you have these error bars corresponding to standard deviation here grow as you pass through this percolation threshold. And if you look at just the shear modulus, the passive modulus, you'll see a signature of this transition as well, something you might call active stiffening, where the for a large microscopic non-reciprocity here, you have this large peak in the shear modulus at the transition where this peak grows with the microscopic activity, whereas on both sides here, the shear modulus is determined just by the passive links. All right, so one thing you can kind of dig into is why this happens, why this transition occurs, and rather than looking at these honeycomb lattices, it's a little bit easier to think of a triangular lattice that works in much the same way, where essentially what's happening is that if you take one of these monotonic responses at high filling fraction, remove one of the triangles to go into the non-monotonic case, what you see is that you're losing the local force balance. And there's these active forces from the neighboring triangles that now come in at all of these nodes. These active forces, in order to force balance them, deform this previously active triangle that's now passive. This triangle now deforms more than all the ones around it, so it's not affine, but also the active hexagons as a result stop deforming, right? And that's why you lose the active response. The other thing that you can ask that's for the system is that, well, we have all these disordered unpercolated cases, right? And are they really passive, right? I said that they don't have this active modulus. And that's true if you look at low frequencies and you look at their excitation spectra. The excitation spectra have, truly real frequency axis here. But as you go to higher frequencies, as you look at more localized modes here, you see these lobes of imaginary frequencies that would correspond to either if you had an overdamped dynamics, localized oscillations, or instabilities if you had inertia. And so you can recover a signature of the activity here, but only by looking at the at higher frequencies. And you can do this. This works just as well in the ordered systems as it does in the disordered systems. It's just that the lobes look more complicated for these optical phonons. But what's happening is you go through this percolation transition, now going from below percolation here to the percolated case, is that this kind of real frequency gap comes down all the way to the origin, and you have phonons, acoustic phonons that come in with imaginary frequency when you have a macroscopic active response. All right, so maybe to conclude, you might ask, what is this good for? What sort of things can you do? And it turns out that these active materials have all sorts of interesting dynamics. And if you want to design this interesting active dynamics, you need to have this emergent active response. So for example, you have these limit cycles, and these limit cycles synchronize to form these interesting patterns. It's a much more recent preprint of ours that I won't get into now. But then what you can do with these materials is to think about their functionality, how these active mechanical metamaterials can have functionality that's beyond what's possible in the passive case. And in particular, you could have functionality such as locomotion, which is again propelled by these non-reciprocal active components that emerge into a macroscopic response. So this was done experimentally, but I think I'll skip this. I'll just thank our collaborators, Anton Souslov and Jonas Svensson, who did the experiments. The theory was done by Jack Binish and Guido Barding. As I mentioned, the preprints on that. So thank you very much.
Thank you. Thank you. We're planning for a couple of questions. Maybe I can start with one, which is, I was a little bit confused, probably just displaying my ignorance when you were describing the material where you had what you call these active hexagons. wasn't that simply mappable on something which in fact is not active, in which you have two components in the material, one that's more rigid than the other? Or in which way was it really active?
Yeah, it's true. So that's an important point. So first off, if it were, you could program in very, if you were very careful to program in the robots, you could program in something that comes from a potential, right?
Mhm.
And then the theorem that I showed in the beginning that says that your, macro scale response would always be monotonic and your micro scale would still hold. Right. So the special thing about these robots were that they were programmed in such a way that you could not derive these torques from a potential, and essentially you could on some level think of these interactions as coming from curl forces, or forces that have a non-zero curl and therefore not be derived as a gradient.
Yeah, you defined your model in the hydrodynamic in for zero wave numbers, so in the microscopic limit, and I understand that definition, that makes sense to me. And for that reason, you have expanded the stress modulus in terms of the strain. So there's no rotation which is possible. So now could you just speculate what you would have to do if you want to analyze the elastic moduli in reciprocal space, or for localized sort of events, then I suppose you have to expand it in terms of the displacement field to take into account rotations as well, which relax stresses. Is it right?
Yeah, that's correct. And some of the, more detailed model of these odd materials also make contact with, micro rotations and Coursera elasticity, where you could have, kind of passive Coursera moduli, but you could also have these active Coursera moduli, and they can coexist with each other. I think that you would have to expand the strain and the stress tensors both, but you can still have this kind of compare juxtaposition between a symmetric response that's passive and the antisymmetric response that's active, even in that